Hello, good afternoon, students. Today, we are going to start the last topic in the second chapter. So, before that, I want to remind you about the test that we are going to conduct. I have already posted a message in your WhatsApp group, and also I'm going to make sure that you should attend the tomorrow's exam. So, it will give you the clear idea about how the exams will be conducted in the next week. The actual exam will be in the next week, but I'm going to give you some hint how the exam will be conducted. A practice test will be given to you tomorrow. So I will send you the link in the WhatsApp and you can attend the exam. And you have to enter your email ID and also your phone number, preferably the WhatsApp number. So, okay. So let us start the today's topic where we are going to discuss about the energy stored in a capacitor. While discussing about the capacitor, we have mentioning about the capacitor which is capable of storing the energy. It is device used to store the energy. But how much energy does it stores? So that will be discussed today. The first, we are going to consider a capacitor whose capacitance is represented as C. And here, the capacitor will contain two plates, two conducting plates. One of them will be positively charged and the other will be negatively charged. So here, when we consider a charge plus Q, which is residing one of the plates, and on the other plate there will be a charge of minus Q. It is similar to that we are transferring certain amount of charge plus Q amount of charge from negative plate to the positive plate. So it is just like transferring the charge here. The total charge stored by the capacitor is charge deposited on the positive plate. That's why it is similar to that we are transferring the charge Q from one plate to the other plate. Now we are going to find out how much work has been done in order to transfer a charge from negative plate to the positive plate. So that is how we are going to find out the energy. So this work done in transferring the plus Q amount of charge from this plate to the other plate, so that will be stored in the form of energy. That amount of work will be stored in the form of potential energy. But we have to remember that here there is no movement of the charges between the plates of the capacitor directly. Since these two plates are either separated by dielectric medium or the space is completely evacuated. No direct transfer of the charges. The transfer of the charges will be done through the external agency like some cell or the battery, source of energy. And also one more thing that we have to remember is that only the negatively charged particles, which are the electrons, they can move. No positive charges. Positive charges will never move. But here for our convenience, we are going to assume that we are transferring positive charges from one plate to the other plate. So initially, let us assume that, just the assumption, we are going to assume that initially this capacitor, whose capacitance is assumed to be C, and it is a fixed value for a given arrangement. Here, both the plates are electrically neutral. When we charge the capacitor, then we are going to assume that here plus Q amount of charge is transferred from this plate. I will represent it as a second plate and other one is first plate. From the second plate to the first plate. Then what happens? The second plate which loses plus q amount of charges, initially which was neutral, by losing plus q amount of charges, it will become minus q. Other plate by gaining plus q amount of charges, which was earlier electrically neutral, now it become positively charged with a plus q. So that's how we are going to consider here. And also here, this transfer of the charges. Again, I'm going to remind you that here no positive charges can move. We are assuming we are transferring the positive charges. Though actually it is the transfer of the negatively charged electrons. So for we are again considering our convenience. Positive charges more convenient. So that's why positive charges. Assumption. So here we can assume that when the capacitor acquires plus q amount of the charges, this is the maximum charge it can hold when a potential difference of capital V is generated or it will be established between the two plates. So then the relation between the charge deposited, the potential difference between the plates and the capacitance of the capacitor. We already know that equation, which is given by, I will write it here, it will be is equal to C is equal to Q by V. But initially, the charge on each plate, there the capacitor was completely discharged, no charge, zero charge. When there is no charge on the two plates, there is no potential difference. So when Q is equal to 0, then V is also equal to 0. But still, the capacitance is C. It is not equal to 0 by 0, indefinite. No, not like that. It is not charged yet. So that's it. So here, so therefore, in order to transfer, when we are transferring the charge from one plate to the other plate, we are not going to do that in a bulk. We are transferring these charges. Total charge which is transferred is represented as capital Q, but it will be done in very small steps. A small amounts of charge will be continuously transferred from one plate to the another plate. And in each step, the amount of charge which is transferred, since it is very small, it will be represented as either delta Q, or if it is confusing, then we can represent it as a dq. So this is the small amount of charge which will be transferred continuously from one plate to the another plate until the total charge transferred will be is equal to capital Q. Now, when we are transferring the first charge, first installment of the charge, then what happens? There is no potential difference. When there is no potential difference, then there is no electric field between the two plates. Both are at the zero potential, no potential difference. That means electric field is zero. Electric field zero means no opposing force. So therefore, obviously here, the work done in transferring the first installment of the dq is usually zero, that we have seen. But as we go on transferring the charges, then what happens? Here, so this plate, the first plate will become more and more positive. I am representing with the arrow, increasing positive, as well as the other plate will become more and more negative, which indicates that the difference between the potentials, V, it start to build up here. It will increase. When V increase, then electric field will also increase. So that means the opposing force, the force which tries to oppose the further transfer of the charges, increases. So therefore, different installments of the charges dq, when they are transferred from one plate to the other plate, so gradually the opposition for them increases. That's why here we are dealing with a variable force, not a constant force. So that's why it might have just remind you that which method we have to use to find out the expression for the total amount of work done. Yes, of course, we are going to use integration methods. Okay, we are going to use the integration methods. So now, before starting the actual derivation, the sum of the point I'm going to make it clear. So first thing is that here, initially the capacitor is 0. When the, sorry, charge is 0, so for capacitance is a constant, and the maximum charge it can acquire is capital Q. Capacitance is represented as C. The maximum potential difference is represented as V. Or in other words, we are saying that when a maximum potential difference of V is applied between the two plates by some external source, the charge deposited on the capacitor is capital Q, and its capacitance is represented as C. And here, at some step here, at somewhere, when the potential difference is V, then the electric field between the two plates of the capacitor is represented as E. So when potential difference is V, then field is represented as E. The distance of separation between the two plates, when it is equal to D, the distance of separation, and area cross section of the two plates of the capacitor is represented as capital E. Everything we know that. And also we can establish the relation between each of them here. So we can establish the relation between field and potential. We have derived the expression for the field is equal to V divided by D. Since the field is constant between the two plates of the capacitor, therefore it is equal to the ratio of potential difference between the two plates by 2, the distance between them. And I'm not going to show the negative sign, which just indicates that in the direction of the field, potential decreases. So that's the significance of the negative sign. But here we are concerned only with the magnitude. Okay. So this much we have no. And also, since when the capacitor is completely charged, we know that Q and A, area of cross section, are related. How? So with the help of surface charge density. If we represent the surface charge density as sigma, then we know that the surface charge density is equal to total charge deposited divided by area of cross section. Here we already have imagined that, so the charge is uniformly distributed, no edge effects. So for uniform distribution of the charges. And also for the capacitor, we have seen that sigma and electric field, they are also related. So what is the relation between them? We can represent the electric field in terms of the surface charge density. So what is the expression? So E is equal to sigma divided by epsilon naught. As usual, unless it is mentioned, we are assuming that the dielectric, there is no dielectric. That means everything what we are calculating from the beginning of the first chapter itself, every charge is placed in a free space. So that means here also no dielectric between the two plates of the capacitor. It is, the space is evacuated. So that's why epsilon naught. So this is already what we know. It is more useful. These equations are more useful. Shall we start the derivation? Now, when we start the derivation, we are going to, since we need to use the, so this method of integration, since the variable force has been involved. So that's why what we are going to do, first we are going to take the some intermediate case. The charge deposited on the plates of the capacitor is neither 0 nor the maximum capital Q, but some intermediate value. It is already, we are already begin the charging of the capacitor, So when the value of the positive charge on the first plate is small q plus q, and obviously on the other plate it will be minus q, still the charging is going on, still more installments of the charges in installments of dq is coming to the first plate here. Therefore obviously here when the charge deposited on the first plate is small q, at that point the potential difference between the two plates of the capacitor, so let us represent it as a small v. When charge is maximum, potential difference will be maximum, capital V. But when charge is some intermediate value, q, small q, then potential difference is also not the maximum. It is some intermediate value between 0 and the maximum, capital V. Okay. Now, what happens? In this case, the capacitance of the capacitor, how we can represent the capacitance? When Q is capital, V is capital, C is also capital. When Q is small, not a maximum value, V is also small, that is not a maximum value, and the capacitance is represented as capital C itself, because it is a constant. It does not change. It never changes. It remains as it is. Therefore, at this particular point, we can write capital C constant is equal to charge at that instant divided by potential at that instant, Q by V. So this relation we have seen. Now what we are going to do here, the amount, in order to find out the amount of work done, one more thing that we have to remember is that we are not going to use the relation between the work done and the force and the displacement. We are not going to do that. Here, what is the displacement? We do not know. But we know the relation between the voltage and the, potential difference or the voltage and the work done. The definition of the electric potential. So that is used here. So what is the expression? Here, we can write general expression is represented as if potential difference is V, then it will be is equal to the work done divided by charge, work done per unit charge. So that is the expression here. From this expression, we can rearrange it to find out the work done here. Now, here, since the charge which is deposited already on the capacitor is Q, potential difference is V. So therefore, if we need to add a small additional amount of charge represented as dq, so this then the amount of work done. Remember that here we are going to represent the amount of work done as dw. It is the amount of work done in adding an additional charge of dq when there is already a charge of plus q is deposited on the plates of the capacitor. Okay, when we add the dq amount of charge, of course, the total charge will change, hence total voltage or the potential difference should also change. But since this value is negligibly small, there is no change, almost negligible change in the value of the potential difference. So therefore, when we add this amount of charges to the positive plate, which already has a q amount of charges, V is almost remaining the same. Based on that, we are going to find out the work done here. So instead of W, we have written dW. Here, the voltage is same thing, which is equal to this much, which is equal to small v, and the amount of work done, how much? It will be equal to the charge which has been added here. The charge which has been added, so that is dq. So therefore, it will be represented as V into dq. So this is the expression for the amount of work done in adding dq amount of charge when capacitor already has a plus q amount of charge. Okay, is that clear? Shall we? Do you want me to rephrase it? So again, I will rephrase it. Same thing. It should not be confusing. What situation do we have here? So there is a point. I will represent it as a plus q. Already a plus q amount of charge is there. There is one more point here. From this point, the potential difference between these 2 points is represented as small v. This is the positive plate which already has this amount of charges. Now we are transferring an additional amount of charge dq from the second point to the first point, which are the plates. Okay. So for how much work has been done here? Or the potential difference will be equal to how much? It will be equal to V is equal to, so dW divided by work done divided by the charge which has been transferred. This is not important. We are finding out how much work has been done in order to move this amount of charge from second plate to the first plate. So that is dW. This is the amount of work done. And what is the potential difference between the 2 points? V. How much charge has been transferred? dQ. So therefore, V must be equal to dW by dQ. So that is obtained from the definition of the potential difference. Rearranging that, we have obtained this equation. Now, is that clear? I will continue now. Substitute the value of V from this equation. Where rearranging this equation, we have V is equal to small q divided by capital C. Substitute it here. So for we have dW must be is equal to q divided by C into dq. Okay. C is a constant. We need the total amount of work done. Here we only have how much work has been done in transferring a given installment of dq. But what do we need here? Total amount of work done when all the installments of the charges were given to the capacitor here. They are transferred from one plate to the another plate. So initially, what was the amount of charge on the first plate? It was 0. Then we start sending the installments in dq amounts. So therefore, the total charge deposited on the plate goes on increasing and it reaches a maximum value of capital Q. We have considered some middle step here, somewhere in the middle between 0 and capital Q. So this step has been considered here. So from the beginning itself up to the end, we keep sending dq amount of charges in steps. What is the total amount of work done? So that is obtained by using the integration method. So therefore, total amount of work done will be equal to integration of dw. When we integrate this, dw is equal to q by c into dq. When you integrate this, what is the limit? Initial value of the q is 0. Final value of the small q is capital Q. So we are going to integrate this. And we, of course, know that C is a constant. It does not change. When Q increases, of course, V increases. But the ratio Q by V is always a constant. So it is always a constant. Whatever may be the value. It is a constant. So if C is a constant, so we can take it outside the integration sign. So hence, what do we write here? dw or integration of dw, w is equal to 1 by c into integration of q dq between the limits 0 to capital Q. I am writing each of the step here. So therefore, then what happens here? Integrate it. It is q raised to 1 dq. Or simple one, so directly we can write this. So it will be equal to 1 by c into integration of this. It will be equal to q square divided by 2 between the limits definite integral. So therefore between the limits 0 to capital Q. And this amount of work done is stored in the form of potential energy. So how we will discuss it later. So therefore it will be is equal to 1 by C into Q square, substituting the value of the upper limit divided by 2, or I will take the 2 outside the bracket. So therefore it will be equal to 1 by 2C into Q square minus value of the lower limit is 0. It will be equal to 0 square. So therefore it will be 0 itself, or that should be is equal to 1 divided by 2C into Q square, or I will represent it as a Q square divided by 2C. Okay. So that is the expression for the work done. And also we know that here electrostatic force is what? It is a conservative force. The work done against the conservative force, or work done on the conservative force, it will be stored in the form of potential energy. So that's why the work done will be stored in the form of potential energy. What is the reason behind it? It is the common sense. When work is done against the conservative force, which is electrostatic force, work done will be stored in the form of potential energy. And this much energy will be stored in the capacitor. Okay, this is the derivation. Up to this, you have to do. If you are asked to write, derive the expression for the energy stored in a capacitor, this much you have to do. Simple steps. I have elaborated it. So that's why you can see more steps, more mathematical steps. But actually, what we have done? So we have considered the expression for the electric potential. Based on that, since there is a variable force involved, so then we have used the integration method and substituted the mathematical steps and also value of C. Then finally we have arrived at this expression here. Only 2-step process here. So therefore, this question can be asked for only 3 marks. One for the diagram, the other for the, so this expression, then for the last one for all the other mathematical things. So therefore, you can skip all the unnecessary mathematical steps. If you know it very well, then you can directly skip some of the steps here. That does not make any difference. It is not necessary that you have to write all the steps. You can skip the steps, but it should not, the derivation should never lose its true meaning. Essence should not be lost here. So that is the only thing. So you can write this. Now, at the point where the derivation ends, the actual physics starts. It is only mathematics, nothing but the mathematics. But actual physics begins now. So how do we going to analyze that equation? So that is the question here. So there are various forms in which the expression for the energy stored by the capacitor can be written. So how can we write those expressions? It is by using the relation between the capacitance charge and the potential difference. We know that when the capacitor is completely charged, C will be is equal to maximum charge divided by maximum voltage. And here also we have to remember that with V is determined by the external source. If you are going to change the external source, then obviously V can be increased, hence Q will also increase. But C remains constant. The energy stored, it will remain constant here. So it is depending on the capacitor. So how does it depends on the capacitor? We are going to see that. So now, if we use this equation, C is equal to Q by V, and substitute the value of C in this equation, what do we have? So U should be is equal to Q square divided by 2 into C, which is equal to Q divided by V, and since by rearranging M, V goes to the numerator. Therefore, Q and Q get cancelled. Therefore, this expression can be written as how much? Q into V divided by 2. So, therefore, it will be equal to 1 by 2 QV. The another way in which this expression for the energy stored, same expression can also be represented like this in terms of charge and the potential difference. This is in terms of charge and the capacitance. Similarly, if we substitute the value of Q instead of C in the same equation, then what happens? The energy stored U will be equal to, now we are going to substitute the value of Q from this equation. Q is equal to C into V. Substitute that here. So therefore, it will be equal to Q square. So therefore, it will be equal to CV square divided by 2C, which is equal to C square into V square divided by 2C. 1C in the denominator and 1 on the numerator cancels each other. Remaining is half into C into V square. All these three are the expression representing the energy stored by the capacitor. U is equal to, either we can write it will be equal to Q square by 2C, or it will be equal to half QV, or it is equal to half CV square. One and the same, three different forms. These equations are useful while solving the numerical problems. They are representing the same thing, but in different terms here, different physical quantities. Energy stored in terms of the charge and the capacitance. Energy stored in terms of the charge and the potential difference. Energy stored in terms of the capacitance and the potential difference. In the numerical problems, any values may be given to find out the energy stored. So they may give you the value of charge and the capacitance. Then you have to pick the suitable equation. Capacitance and charge means this equation. If capacitance is given, voltage is given, this equation. If voltage is given, charge is given, not capacitance, then this equation. So therefore, it is easy to remember all these equations. Different forms of the equations has been explained now. Now, there is one more thing. We are going to use the general case. How much energy is stored by a charge configuration, not only the capacitors, parallel plate capacitor, any charge configuration, in terms of the electric field. We will do that. The derivation is not yet asked, but you have to remember that meaning here. It is more generalized case. When we are considering the generalized case, so then it will be useful in solving the numerical problems. Maybe it is more useful than in the board exam in some competitive exams. So therefore, we are going to discuss it. Derivation is not necessary, but look at the derivation, how we are obtained this expression here. Once we look at the derivation and understand it, then it will be easier for us to remember it for longer time. Retention will be longer. The memory will be stronger here. So that's why we are going to do that. Now, consider any form, whatever form you may take. But here, we have to express the energy stored by the parallel plate capacitor in terms of the electric field. Remember that in final expression, there is only electric field E is present. All these terms, whether it is Q, C, V, do not appear. Our objective is to eliminate all these terms here. How do we do that? Using these set of knowledge we have already gained. You can choose any equation. It does not make any difference here. Any one of these three forms can be used here. I will use this equation, which is containing only Q and V. Okay. So therefore, we know the expression for the energy stored by the parallel plate capacitor given by the equation 1 by 2 Q into V. We have to substitute the value of V so that we will get the relation of V with electric field. We are going to use this equation. V is equal to E into D. We are going to do that. So this will be equal to half into Q. I have not written that yet. But instead of V, we are going to write it is equal to E into D. E into D. But here we also do not need the Q. We have to replace it with something else. Which one? We are going to make use of this equation. Surface charge density will be equal to Q by A. So for if you are going to rearrange it, Q will be equal to sigma into A, where sigma is the surface charge density and A is the area of cross section of the capacitor. D is the distance between the plates of the capacitor. A is its area of cross section. E is the electric field between the two plates. But still, we also do not need sigma. What do we need here? Electric field only. So therefore, we are going to make use of this equation. E is equal to sigma by epsilon naught. So therefore, sigma must be equal to epsilon naught into E. So therefore, potential energy stored, so that will be equal to half into, I will take sigma is equal to epsilon naught into E. I will write the area of cross section here into E into D. So E into E square. Energy stored will be equal to half epsilon naught into E square. Then these two terms, D into A, the distance between the two plates, and their area of cross section. What does it represent? It represents the volume of the space between the plates of the capacitor. Area of the plates into distance between the two plates. It is represents the volume between the two plates of the capacitor. So for I will represent it as a V dash, or I will just write it as a volume. So this is the expression for the potential energy stored by a parallel plate capacitor in terms of the electric field. It is equal to half into epsilon naught into E square into the volume of the space between the capacitor plates. But we can generalize it even more. I am going to take the volume on the other side of the equation. I will write it will be equal to potential energy, U, which is nothing but the potential energy divided by volume. What does it mean? Charge by area or charge by volume. Mass by volume. What does it mean? It means density. Which density? Numerator. It is energy density. So this energy density is represented by small u. Potential energy per unit volume. What is its value? The potential energy is this much divided by volume. Volume can cancel. Remaining term is half epsilon naught E square. Potential or energy density of a given charge configuration. It is, even though we had derived this expression for, so this parallel plate capacitor, but this equation is even more generalized equation. We in the expression u small u equal to half epsilon naught E square, we cannot see anything. capacitance or charge, nothing, only field and the medium, nothing else. So therefore, so this equation can be extended to any charge configuration here, not necessarily a parallel plate capacitor. It can be extended to so some spherical capacitor or a conductor or something else where there are some point charges distributed over a given space. Then at any point, the energy density will be given by this equation. If electric field is null, at that point, the energy density will be given by this equation. Even the charges are distributed in a given medium with epsilon naught, with the permittivity other than that of the free space. Then the expression for the energy density will be written as half epsilon into E square, or it will be equal to half K into epsilon naught into E square. Simple like that here. So it can be generalized here to any charges here, any charge distribution or any charge configuration. Okay. So here, while discussing this topic, we have understood that in case of the, just when we consider the parallel plate capacitor itself, we have understood that here electrostatic force, since it is a conservative force, it is not important that how the charges are transferred from one plate to the other plate. Either they have been done directly or via through some external agency, it does not make any difference. Since for a conservative force, work done, it will be independent of the path followed. It depends only on the initial and the final position. So therefore, so this energy stored will be depending on how much charge is stored. So that's it. But how it is stored? No. Only depends on the Q. By which manner we are depositing the charges, transferring the charges, not interest. We are not interested in it. Energy is not interested here. So therefore, it is a potential energy. This amount of charge is deposited. It is transferred from one plate to another plate. But by how? By which means? Not important. And also, so one more thing, so which I have seen is that the energy density, the energy stored per unit volume is independent of the charge configuration here. So independent of the charge configuration means it can be extended to any kind of charge configuration. Only depends on the electric field. Whatever may be the shape, the configuration is fixed, then energy stored is fixed. So therefore, these equations are important. Remember that the derivation of this equation for the energy stored by the parallel plate capacitor is important, but the derivation for the energy density is not asked until now. But the expression for the electric field or energy density has been asked. Mention the expression for energy density in terms of the electric field. So then you have to write this equation and explain the terms. That means when we are explaining the terms, we have to write what does epsilon naught means. It is permittivity of the free space. What does E means? It is electric field. So that's it. So that's the explanation. We do not need to explain everything. One mass explanations, that's much here. We have to explain the terms involved only, not the equation, terms involved. When you are asked to write the, mention the expression, we only need to mention or explain what are the terms which appear in the given equation. What does they mean? Not we are going to explain the equation. So with this, we have completed the second chapter. If you are following the textbook, you might also see another last portion, Van de Graaff generator. This has been removed from the syllabus from the last year itself, not because of the coronavirus. It has been already removed from the last year. So therefore, we are not going to discuss it, whether they are going to change the syllabus or remove some of the topics in this year or not. Van de Graaff generator has been already removed last year itself. So we are not bothered about that. And also it is a simple device which is used to develop high potential by spending very small amount of energy. Using the simple fact that in a given sphere, always inner, sorry, inner sphere will be always at the higher potential than the outer sphere. So that phenomena will be used here. Whatever may be the charge deposited on the outer sphere, inner sphere will be at higher potential. So that simple principle is used in building very high potential to accelerate the charges. Then that accelerated charges will be used for many cases here. Even if you Google it by typing Van de Graaff generator, you might see a very funny applications of the Van de Graaff generator. In huge malls, even the Van de Graaff generator will be kept. And if you place the hand above it, it will charge you. And it will be indicated by the your hairs, which will be, it will look like an antenna. You will start to look like an alien with a straight hairs pointing in all directions. Not all the hairs, some of the hairs. If you have a dry hair. So then that is not in the syllabus. So let us not discuss about this. So derivation is simple. Again, be prepared for the examination. Tomorrow I will send a practice test which is containing only 3 questions and some basic information you need to fill. Roll number, your name, email ID, and also phone number. And with the 3 different questions, different types of the questions, where there is a multiple choice question and also a small answer question, short answer questions with a single word, and also a single sentence. Only 3 different types of questions will be there. A small 1 sentence, 1 word, and multiple choice. So thank you for attending the class.